All right, we just learned this amazing new power, the derivatives of sine and cosine, and let's use them. I bet you could do these two examples without me telling you how. Take a second, pause the video, give it a try. I am going to cruise right along. So derivatives are linear because our limit laws are linear. That means that we can leave this 4 out front and take the derivative of sine to get cosine. Not only that, because these two terms are totally separated by a plus sign, we can just do them separately, which is pretty amazing. So I'm going to get a 2, and I want to get the derivative of cosine is negative sine, which means we need to ask ourselves what to do with that negative, and it's going to turn that plus into a minus. All right, next up, something a little harder. Because we have not a plus but a times, we need to use a rule. It starts with a p. That's right, the product rule. Let's go ahead and take the derivative of the first term. That's going to be a cosine of x. Leave the cosine alone. Plus, leave the sine alone. And we want to take the derivative of cosine is negative sine of x. Very nice. How could we not clean that up? Look at how nice that is. Let's clean that up. That cosine times cosine is cosine squared, which we normally write like this, rather than doing a big parentheses. And then that minus is going to come out. All right, let's do a little reminder, in case we haven't seen this in a little bit of notation. Cosine squared of x is equal to cosine of x squared. It is not the same thing as cosine of x squared. So these two are definitely not equal. All right, we're squaring the whole thing. So, little friendly reminder on notation. Okay. That was fun. Hopefully that worked out. Here is another friendly reminder of something from Trig that you may have forgotten that's going to help us out very shortly here. The Pythagorean identity. The Pythagorean identity. If there is one Trig identity you actually need to know and use, it's definitely the Pythagorean identity. So, if we recalled from way back when, let's scroll up to this amazing unit circle. We had this right triangle, but also our unit circle up here. On this right triangle, there is something that is true for us, for all right triangles, involving the name Pythagoras. So the thing I know from Pythagoras is that a squared plus b squared is equal to c squared, where c has to be the hypotenuse. So if you square the legs of a hypotenuse and you add them together, you get the square of the hypotenuse. But we just said that those legs, that width and that height, are given by sine and cosine. So the Pythagorean identity is sine squared x plus cosine squared x equals, what was the hypotenuse on a unit circle? That's right, that's the radius, so that's a 1. Very nice. Sine squared plus cosine squared equals 1. It is by far the most important trig identity. It relates it right back to those right triangles. So that is the Pythagorean identity. We are going to need that more than you would think. Plus, from there, you get a couple extras for free. So let's just see what happens if I were to divide everything by sine squared. So if I took, sine squared plus cosine squared equals 1, forgive me for dropping my x's, and I divide everything by sine squared, oops, helps if I do sine, not cosine. What do I get out? Well, these would cancel, and I get a 1 plus cosine squared over sine squared. That's cosine over sine all squared. Cosine over sine is cotangent squared. 1 over sine squared. 1 over sine is cosecant squared. Nice. That would be That's a hard one to remember. 1 plus cotangent squared equals cosecant squared. I don't really memorize it. I just memorize the Pythagorean identity, and then I divide to remind myself. In fact, we could do this again, but instead of dividing by sine squared, I could divide by cosine squared. And you could probably see where this is going. Sine squared over cosine squared, that's sine over cosine all squared. That is going to be tangent squared plus 1 is equal to 1 over cosine is secant. So that's going to be secant squared. Yeah, tan squared plus 1 is secant squared, sometimes just written as secant squared minus 1 is tan squared. Point being, if you just remember that Pythagorean identity, which makes sense if you know your right triangles, then these other seemingly mysterious identities just pop right out from that. Okay, I need to remind you of that because we're going to use it right now. How do we get the derivatives of all of these other amazing trig functions? Well, we just said tangent is equal to sine over cosine. And we just said that secant is equal to 1 over cosine. And we said cotangent is equal to cosine over sine. And we said cosecant is equal to 1 over sine. And we know sines and cosines, so we should be able to get the derivative just using this. If only there was some rule that helped us take the derivative when we had fractions. Some rule when we were dividing or had some kind of a quotient. Oh, that's right, the quotient rule. Let's go ahead and see if we can figure this out real quick here. Let's do 1 or 2, and then I will probably leave the rest up to you. I wanted to take the derivative of tangent. That is just the derivative of sine over cosine. Let me add some x's in there. Okay. Let's do it. Let's do our quotient rule on this. So I would take the derivative of sine is cosine. Leave the cosine alone. Minus, take the derivative of, rather leave the sine alone. Derivative of cosine is negative sine all over cosine squared x. Squaring that whole thing. Don't square the x. We're squaring all of cosine of x. All right, take a second, see if you can clean this up. See if you can use that identity to make this a little bit nicer. I'm going to do it right here. So cosine times cosine is cosine squared of x. Minus minus is going to be a plus. Looks like sine squared of x all over cosine squared of x. All right. Hopefully from here you can clean it up. We just talked about this. It's going to be 1 over cosine squared of x. 1 over cosine squared. What is 1 over cosine? Secant. This is going to be secant squared of x. Fantastic. The derivative of tangent of x is secant squared. Amazing. Whether that's of theta or of x, the derivative of tangent is secant squared. Yes, you need to know that. Yes, it'd be good if you knew how we got it too. But most of the time we can just remember that it's secant squared. All right, let's do one more. Let's go ahead and do the secant. So I'm going to take dx of, for secant, looks like 1 over cosine of x. Same game, we're going to do the quotient rule. So if I do the quotient rule, this one is in some ways nicer. The derivative of the top is just a 0, and then I leave the bottom alone, but it's not really going to matter. Minus, leave the top alone, that's just a 1. Times the derivative of cosine, is hopefully getting to be automatic, negative sine. All over its cosine squared again. Great. If I clean that up, it looks like what I get is I get a 0 minus minus is a plus, so just a sine of x over cosine squared x. That's not that bad. Sine of x times over cosine squared of x, but I think I could write this better. That looks to me like 1 over cosine of x times sine of x over cosine of x. I just pulled out that cosine because I saw that sine and cosine. I was like, I bet I could make a tangent. I bet I can make a tangent out of that if I can just pull one cosine out. And I can. 1 over cosine secant x times sine over cosine is tangent x. And look, I've written this without any fractions. Secant x tangent x. So the derivative of secant is secant x tangent x. Fantastic. Or he'll write it in the shorthand that we've been writing the other ones in, secant tangent. Nice. Not too bad. Not too bad. Maybe take a second, see if you can work through the last two. You can pause the video. All right. Maybe you gave those a shot. I'm going to fill these in rather than go through all of them. So cotangent is going to, we're going to get a negative out of this, and we get a negative cosecant squared, kind of like our secant squared. For tangent, we get this negative, and we switch to cosecant. Cosecant, we get, again, a negative for that and then we get cosecant cotangent. So similar pattern, right? Our cosine, our cosecant, and our cotangent, they all get a negative. Maybe one of those reasons why you would want a co for all of those. Great. Now we have a lot more power. We have all those trig functions to work with, and we will give some more examples on the next lesson.